At the beginning of time, at the instant of the Big Bang, there was a single, all-embracing force of unparalleled power. As the universe cooled, this superforce lost its unity and divided into the forces and particles of our universe. Today, physicists are searching for the basic law that could uncover that lost unity. In fact, this was the lifelong goal of the most famous physicist of our time, Albert Einstein. Einstein gave the world a new theory of gravity and produced the equation that revolutionized physics, E=mc². Yet the greater part of his life was spent trying to extend his ideas into a complete description of all phenomena. Einstein did not succeed. But now, finally, we may be on the brink of uncovering for ourselves what Einstein never knew.
Major funding for NOVA is provided by this station and other public television stations nationwide. Additional funding was provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials.
In the beginning, when space and time started in the hot fireball we call the Big Bang, the whole universe could be described by a single all-embracing law. But as time passed, the universe cooled. Simplicity became complexity, and the familiar world developed of change and diversity. Today, the original simplicity has vanished from sight, but maybe it could be recaptured if the fundamental laws of matter could be worked out. The discovery of an all-embracing law is a goal which physicists have sought throughout history, a single, complete theory to explain all physical phenomena, life, the universe, and everything. According to a new generation of physicists, we may now be close to discovering that original simplicity, finding the all-embracing law which would tie all physics together.
And then the fact that this is equal to plus this, I choose to be a boson.
I think it's an enormously healthy time in physics. The controversies are very, very productive, and eventually this may work out, and we will find out what the real theory of the universe is.
This is a boson and this is a fermion.
So I think what happens here is that you have people who really feel that they are learning something about the universe here. People are excited. They feel that new physics is opening up. People want to leave their mark in physics, and they feel that, in fact, there is a chance here that this is important.
Today's physicists are coming up with ever more daring theories, encompassing more fundamental ideas. And this approach is leading them farther away from direct experimental testing. In fact, physics may be facing a dilemma. As physicists finally approach the ultimate theory, so they may lose contact with the experimental tools that have traditionally unlocked nature's secrets. New machines for direct testing will require temperatures so high that they may be physically impossible to construct. And as the goal of unification gets ever nearer, physicists may have to rely more and more on the mathematical elegance and inner simplicity of their theories alone. If ever a scientist believed in the power of aesthetics to produce truth, it was Albert Einstein. He's most famous for the theory of general relativity, a totally new way of understanding gravity. Yet the greater part of his working life was spent trying to extend his ideas into a complete description of all phenomena, as he called it, a unified field theory. In 1928, the equations of Einstein's latest attempt at unification were even posted in the windows of Selfridge's, the famous London store. Crowds gathered to look at them. But Selfridge's was overconfident. Einstein's equations for a unified theory never quite worked out. The most famous scientist in history died knowing that his life's goal was unrealized. But since Einstein, the search for a single fundamental theory has continued. It's a story that takes us to the limit of experiment. Deep underground, where giant tanks of water are waiting for evidence of an extremely rare occurrence, the decay of a proton. And out into the wider universe in search of missing neutrinos, thought to have been created 15 billion years ago by the Big Bang. And down into the innermost parts of the atom, where particle accelerators collide matter and antimatter in tiny recreations of the start of the universe. Science has known for 100 years that all the objects in the world are made up of the same sort of particles. A tree is a complex arrangement of atoms and molecules, but all the constituent parts are known. Scaled down some 1,000 times, we see the individual cells and fibers. Smaller as much again are individual molecules. Each atom reveals layers of electrons around a nucleus of tightly packed protons and neutrons. And at the smallest level known, there are quarks, which make up each proton or neutron. And there are also electrons which orbit the nucleus. We can also look outwards to the farthest reaches of the universe. 1 million trees would barely span our own Earth. The Earth and solar system itself are but tiny specks within a complex of galaxies. And galaxies in their turn are mere dots in the full span of the universe. We can now trace the history of our universe back to 1/1000th of a second after the Big Bang, when the universe was a hot soup of fundamental particles and forces. Physicists regard each tiny particle found today as a fossil record of that explosive instant. But at the moment, the most important characters in the story are not the particles themselves, but the forces which hold matter together and are the source of all change and motion. Scientists today recognize 4 of them. Gravity is the dominant force. Nothing in the cosmos escapes it. It keeps the planets in their orbits and holds the galaxies together. The electromagnetic force is familiar to us as light and radio waves. It also binds atoms together into molecules and electrons to the nuclei of atoms. Gravity and electromagnetism were the only forces known until the 1940s, when 2 new forces were found, operating at the tiniest distances, actually within the nuclei of atoms. The weak force is responsible for the slow disintegration of the atomic nuclei, which causes radioactive decay. We can also see the force in action during the cataclysmic explosion of an aging star, a supernova. The strong force, also a recent discovery, actually holds the nucleus of the atom together, making ordinary matter possible. This force is so strong that the nucleus is 1,000,000 times harder to break apart than the atom itself. The goal of an ultimate theory is to show that these 4 very different forces are in fact related, that in the distant fireball of the Big Bang, they were unified into one primal force. The belief is that as energy and temperature approach those of the Big Bang, the once separate forces blend, become equal in strength, and reveal their hidden unity. No known accelerator experiment will ever be able to journey into the far regions where all 4 forces are unified. The energies required are just too high. But there may be stepping stones which will point the way to a full synthesis. And in fact, one theory has already taken the first momentous step. a connection has been made between two of the forces, the electromagnetic and the weak force. A new monument has been added to the landscape. But it took over 10 years for three theoretical physicists, each working independently, to sketch out just how these two forces were linked. In 1960, Sheldon Glashow took the first step. Then Stephen Weinberg and Abdus Salam proposed a mathematically consistent theory in 1967. The model they developed is known as the electroweak theory. Their work was initially ignored because the theory did not yield testable results. However, slowly, enough experimental evidence did accumulate so that the three were jointly awarded the Nobel Prize for Physics in 1979. The Nobel Prize is a distinguished award, but not definitive proof of a theory. There was more to be done.
Involving products of coupling constants and operators.
Weinberg himself knew what was needed to convince the skeptics among his peers.
We have to do all sorts of things. So we have to discover the W and the Z boson, for example, which will be done in April in Geneva.
Carlo Rubbia, an experimental physicist, took on the job of finding the W and Z bosons, two new subatomic particles predicted by the electroweak theory.
We're now in the countdown.
In 1982, the European Laboratory for Particle Physics in Geneva, known as CERN, was the site of a spectacular collaboration involving hundreds of the world's top research physicists. The particle accelerator at CERN was built to accelerate beams of protons around its 4-mile circumference almost to the speed of light and then smash them against a fixed target. The extreme heat or high-energy states which result from these collisions yield traces of subatomic particles which can be seen in no other way.
First proton injection.
The problem was, in order to find the W and the Z particles, Rubbia and his colleagues knew they had to generate a collision that would create temperatures 100 times higher than were currently possible.
Second proton injection.
Rather than smash the proton beams against a fixed target, Rubbia's inspiration was to use the same accelerator to guide a second beam of negatively charged antiprotons in the opposite direction.
You must give us the last antiproton interlock condition, and the antiprotons are in.
Since the proton and the antiproton have exactly the same mass and equal but opposite charges, the magnets of the accelerator can guide them in equal but opposite directions and accelerate them both nearly to the speed of light. When these two particles collide, if the impact is just right, they annihilate each other in a great explosion. Much of the energy of the explosion is converted into matter, creating new particles that fly apart, leaving mere traces of their fleeting existence. It's from the direction, velocity, and shape of these tracks that the particles themselves are deduced.
This is a very spectacular event. You see a very energetic track emerging from the vertex here in this direction, and it's emerging at a large angle to the incident proton-antiproton direction. This is exactly what we would expect if we had a W produced in the center here.
The experiment not only proved the existence of the W and Z particles, but showed that they had exactly the mass predicted by the electroweak theory.
It's high mass stuff.
Very high mass. The transverse energy is small. It's only 10 GeV.
In 1984, the Nobel Prize for Physics was shared this time by experimental physicist Carlo Rubbia and CERN's senior engineer, Simon van der Meer. In physics, theory and experiment are intimately connected. Here, theory provoked experiment. Inspired by the electroweak theory, the CERN team figured out how to expand the limits of technology. They were able to create a high-energy collision, which allowed the two forces to display their common ancestry, just long enough to confirm twofold unification. The internal consistency of the theory, combined with experimental verification, has led to an almost universal acceptance of the electroweak connection. But the goal is to unite all the forces. So the next step is to go beyond twofold unification to develop a theory which predicts that at even higher energies, there is a more distant monument, one which brings the strong force into the scheme and unites it with the weak and electromagnetic into a threefold link. It's unlikely any accelerator team of the future would be able to confirm such a theory. They would need a machine so powerful that with today's technology, it would have to be as large as the Earth itself. With dim prospects for such colossal machines, physicists may become ever more dependent on their theories alone. One important theoretical tool which is being used to unravel the link between forces and predict new particles is the concept of symmetry. Symmetry is a familiar idea from everyday life. We see it in nature and art. But in science, it has a slightly wider meaning. To best understand this, we must forget our preconceptions and embrace a new definition. A checkerboard remains a checkerboard even when the black and white squares are interchanged. This is the way to imagine symmetry in science. We transform a system in some way and it ends up looking the same. The symmetric ice crystal can be rotated, and although the frame is moved, the drawing still looks the same. Just like the checkerboard. This simple idea of symmetry has far-reaching results. To understand the whole universe, there must be laws which are true everywhere, on the moon, for example, and on Earth as well. That's a constraint on all theories. They must be symmetric between any two places. Einstein looked at the universe and imposed another symmetry. He required that the laws of nature be the same for an observer standing still as for someone moving at constant speed. This symmetry led to a revolution in thought and a new way of looking at space and time called special relativity. And out of this has come the famous formula E equals mc squared. But Einstein went one step further. He demanded that the laws of nature also be the same for an accelerating observer. He had recognized a new symmetry. He had seen how the effect of gravity on an object was indistinguishable from the effect of acceleration. This recognition enabled him to create one of the most beautiful scientific works of our time, Einstein's theory of general relativity, essentially the product of the simple idea of symmetry. But if there is as much symmetry in nature as physicists claim, why is it not more apparent? This can be understood by the principle of hidden symmetry. To see how symmetries can be hidden, let's think of an ordinary magnet. When we heat up the magnet to a very high temperature, it loses its magnetism and becomes a lump of metal. No North Pole or South Pole, uniform throughout. A tiny scientist living inside this lump of metal would see the individual magnetic particles as a random yet symmetrical arrangement. No matter how the magnet world was rotated, she would see the same pattern. To her, this is symmetry. But if we cool the magnet, its individual magnetic particles line up in a particular direction. The magnet chooses a north and south pole. Now, as our scientist surveys her domain, in one direction she sees the blue ends of the magnet particles. And when the magnet rotates, she sees the red end instead. Although in the cold magnet there seems to be more order, in fact, the magnet has lost the symmetry of rotation. The perfect symmetry that had been obvious at high temperatures is now hidden. The laws of physics haven't changed, even though the state of the magnet has. Physicists believe, as with the formation of the north and south poles in a magnet, that the four forces came into being as the universe cooled, hiding the perfect symmetry of the Big Bang. Although the goal is to ultimately unify the four forces, they are finding that even threefold unification is a distant landmark. The theories which unite the strong, electromagnetic, and weak forces are called grand unified theories. There's no machine powerful enough to test them in the same way that the electroweak force was tested at CERN. But the grand unified theories do make three concrete predictions about the existence of matter that don't require high energies for confirmation. If any one were found to be true, it would be strong evidence that physics is on the right track. The first and perhaps most startling is the prediction that the basic building block of matter, the proton, should decay. Such decay is predicted by the symmetry principle. It works like this. Different particles are affected by different forces. For example, quarks are affected by the strong force, which binds them into protons, while electrons feel only the electroweak force. So if these two forces are linked by symmetry, then the particles are as well. So quarks and electrons must be interchangeable. A proton is a combination of three quarks. If one were to be replaced by an electron, the other two remaining would no longer make up a proton, and the particle would literally fly apart. Since nearly everything in the universe is made up of protons, the unification theory implies that given enough time, our entire world will disintegrate. It sounds alarming, but the process is so rare that in this tank of water, only 1 or 2 protons are expected to decay a month. The experimenters hope that by waiting and watching long enough, they'll be able to spot a proton breaking up and sending off photons, or tiny flashes of light, to the 2048 sensitive phototubes lining the walls. It's a long wait. In fact, a team from the University of Michigan, the University of California at Irvine, and the Brookhaven Laboratory has been standing by to observe a decay since the summer of 1982.
Okay, so we can then shut off this run.
The snag is that cosmic rays may mimic the process. So the IMB team buries its experiments on 2,000 feet underground in the caves of a salt mine near Lake Erie. Several similar experiments have found homes in equally exotic surroundings. But even at these depths, some unwanted particles still get through. At the University of Michigan, computers are busy trying to spot the rare patterns of light that would signal proton decay. A reconstruction of exactly when each phototube was hit reveals some quite distinctive features. But are they what's expected? Proton decay should be recognizable by characteristic back-to-back signals, the light from which will illuminate just a few phototubes in any cross-section of the tank. There are 2 types of cosmic ray particles which produce signals that can confuse the experimenters. One of these is the muon, produced high in the atmosphere. Thousands of these penetrate the tank each day. Its signal appears as complete walls of phototubes lit up in a continuous swath of light. The second offending particle, the neutrino, interacts with the water and produces a light pattern very similar to proton decay. Since 1982, millions of events have been recorded. Most are unwanted background. But what of the remainder?
The experiment's gone extremely well. We have not found the expected events which were on the simplest version of grand unified theories. This is a little bit disappointing and somewhat embarrassing to the theoreticians, but I would say at this moment it doesn't rule them out, but it's a little bit embarrassing for them.
So far, the evidence for proton decay remains inconclusive. The second prediction of the grand unified theories is the existence of an unusual particle called a magnetic monopole. Sheldon Glashow explains.
When Maxwell made his theory that put together electricity and magnetism, he noticed something. He noticed that there could exist particles that have an electric charge that are the sources of electric fields. A few years after his theory, these particles were discovered. They are called electrons. There could also exist particles that are the sources of magnetic fields, from which magnetic fields come. He imagined that those particles also exist, but it seems they don't, or at least until the present day, nobody has ever found a particle from which magnetic field comes. If I may make a picture on this piece of cork, an electron, for example, E for electron, is a source of electric field. That means coming from it, there's an electric field that points out in all different directions. Now, a magnetic monopole is exactly the same thing. It's a fundamental particle which is the source of magnetic field lines. A magnetic monopole, a hypothetical particle, from which magnetic lines of force would come out in all directions. Now, the only kinds of magnetic systems we can make are things that look like this, magnets. Magnets are things that have a north pole and a south pole. They do produce a magnetic field, but the magnetic field comes from one side and goes to the other. It has lines of force that look like this. Now, what a magnetic monopole is a north pole without an associated south pole. So you might say, that's simple, just break the magnet in half and you have a north pole and a south pole. But it doesn't work like that, because a north pole is created here and the south pole is created here, and you end up with a smaller magnet. You can imagine doing this again and again, continually cutting a magnet into smaller pieces. You finally end up with a single atom, which is also a magnet, but it too has a north pole on one side and a south pole on the other. You can tear the atom apart. You end up with an electron. The electron is also a magnet, but it has both a north pole and a south pole.
According to threefold unification, these monopoles would be very heavy particles, so heavy that current accelerators are unable to create them. You'd need an accelerator 100 trillion times hotter than what we have today.
There was an accelerator of just that kind once, and only once, in the history of the universe. The original Big Bang, the tremendous explosion from which our universe evolved and is still exploding, this explosion was of an immense energy, far beyond any energy we can produce or will produce in the laboratory. It was energetic enough to make magnetic monopoles, if there are such things.
If such exotic particles do exist, where does one start to look for them? Do physicists have any guidelines?
Now, the logic that is employed in this search is that which the French call the logic of the lamppost, which goes as follows. Suppose you go back to your home at night, a little drunk and walking, and when you get to your doorstep, you find that you have lost your keys. Where are you going to go back and look for your keys? Well, you will look for your keys under the lamppost, because should they be in the dark, you wouldn't find them anyway.
The best place to find monopoles seems to be underground, where researchers also look for proton decay. Monopoles flying through matter are expected to trigger or catalyze the decay of a number of nucleons.
Imagine a monopole moving through the detector, catalyzes one nucleon decay, catalyzes another nucleon decay, and so on. So we would see a sequence of nucleon decays separated by a short time interval. And that's a very characteristic signal. We look for that. We haven't found any evidence for it.
But the fact that no monopoles have been found is not conclusive evidence that the grand unified theories are wrong. After all, no one knows how many monopoles there are or where in the universe they might be. The third prediction from the grand unified theories concerns the ever-elusive neutrino. This particle, produced by nuclear reactions in the sun, was originally thought to have no mass at all, like a photon of light. But recent work suggests that it may have a mass after all. Some scientists are now going to great lengths to measure it. One of the best places to look for neutrinos is under the core of a pressurized water reactor. Such nuclear power generators provide an abundant and controlled source of neutrinos. If a neutrino is found to have any mass at all, it would support not only threefold unification, but also theories about the fate of the entire universe as well.
Many neutrinos were left over from the Big Bang, and it is possible that they have clustered around galaxies and are flying like moons if they have a non-zero mass around the galaxy. So it is possible that the galaxies are actually ensembles of neutrinos, more than anything else, with a little bit of ordinary matter in the middle. On the other hand, for the universe as a whole, you know that we believe it started in a Big Bang, we still see the galaxies flying away from each other as a consequence of this original bang. Now, there is a force opposing the separation of the galaxies, and that is the gravitational force of each galaxy onto each other that is trying to stop the expansion. And there are three possibilities. Either the explosion was so energetic that the galaxies will fly forever apart because the mass in between them is not enough to recollapse them, or the in-between possibilities where the galaxies will separate till they eventually come to stop. Or there is enough mass to have the galaxies eventually come back. Those are an open, a flat, or a closed universe. Now, if neutrinos do have masses, since we believe many of them were made in the Big Bang, about 1,000 million neutrinos per atom of ordinary hydrogen, it is enough that they have a very, very tiny mass to contribute so much to the mass, overall mass of the universe, that the neutrinos themselves will pull the galaxies back eventually. So the fate of the universe depends on very few things, and one of them is whether neutrinos have a mass or they don't.
Perhaps the most promising measurement of the neutrino mass comes from a Soviet experiment undertaken at the Moscow Institute for Theoretical and Experimental Physics. In 1984, they concluded that the neutrino seems indeed to have a mass 1/10,000th that of an electron. To date, no one has been able to duplicate this experiment. The conclusions are tantalizing, but not as yet confirmed. The results of all the experiments on threefold unification are so far inconclusive. No protons have yet decayed. No monopoles have come through our detectors, and the neutrino mass experiments remain tentative. It seems to a growing number of physicists that they should reject the constraints of the experimental lamplight, which allows them to look only in certain places. They believe that substantial further progress can only come about by seeking an even more ambitious fourfold unification of all the forces, including gravity. To do this, they have to imagine energies beyond even the still unconfirmed point of threefold unification, because only there can one imagine that gravity will show any unity with the other forces. To go this far is not only to go way beyond experimental testing, but also to encounter immense difficulties in the theory. After all, the attempt to include gravity eluded even Einstein. But that story may have an ironic twist. In 1919, the very year that Einstein achieved world fame, Theodor Kaluza, a young German physicist, made a remarkable discovery. He took Einstein's equations of gravity and wrote them down as if they applied to a different world. Not the four-dimensional world of Einstein, but a mathematical universe with an extra fifth dimension.
To his amazement, he discovered that he had actually, when rubbing off the fifth dimension, the fifth coordinate, explicitly from the equations, he found that he had written down not only the theory of Einstein's gravity in 4 dimensions, the normal gravity, but also Maxwell's electromagnetism on the right-hand side of the equations. And so this was the first unification of Maxwell's electromagnetism with Einstein's gravity, achieved by extending space and time to 5 dimensions rather than 4. An incredible and a miraculous idea.
In mathematics, an extra dimension is a matter of algebra. One dimension,
and then my father did something about it, sent it to Einstein. Einstein repeated or asked another question, and so on. There are 5 or 6 letters of this sort.
And then suddenly, in October 1921, 2.5 years later, he writes himself to Kaluza saying, "I am now having second thoughts about having restrained you from publishing your idea on a unification of gravitation and electricity 2 years ago. I wish I shall present your paper, if you wish, I shall present your paper to the Academy after all." And then he did.
Kaluza's idea was picked up and improved by Oscar Klein in Sweden. But both men lived to see it become little more than an historical curiosity. Kaluza's disappointment must have been enormous. At the moment when he thought he saw how to combine gravity and electromagnetism, it must have seemed impossible to him for it to be merely an accident. His son was a small boy of 9 at the time, and he used to sit in his father's study while he was working. Usually, the father would work quietly by himself.
But one day, it was quite different. He sat completely still for several seconds, and then he whistled very sharply and banged the table. And he stood up, and but he remained completely motionless for several seconds. And then he began to hum an area, or the last part of an area of Figaro. Dum dum da dum dum da 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 dum dum da dum da da dum da.
Equipped with the multidimensional world of Kaluza and the guiding principle of symmetry, physicists have produced daring new theories that attempt to unify not only the 4 forces, but all particles as well. Today, Kaluza-Klein theories have been resurrected in a 10 or 11 dimensional form in connection with a new kind of symmetry, which goes under the grandiose title of supersymmetry. There is hot debate as to whether it's the correct road for theoretical physics to follow. But at the moment, supersymmetry is one of the boldest attempts to produce a single theory of all forces and matter in the universe.
In fact, supersymmetry goes even better than that, because not only is it compatible with the unification of gravity, you can actually show that supersymmetry implies gravity. And in fact, if we didn't already know about Einstein's general theory of relativity, supersymmetry would force us to invent it.
The followers of supersymmetry met in Bonn in 1984. They are here studying the mathematical foundations of a theory which is quite far from experimental verification. But the theories have commanded attention because of their internal beauty. Today, these ideas seem very abstract, and belief in them requires a giant leap of faith. But as the ultimate judge of physics is mathematical consistency in combination with real-world events, these physicists hope that the theory will eventually lead them to make contact with experiment. The ideas in the new theories seem to fit together elegantly, like the pieces of a puzzle. One of the pieces is the multidimensional idea of Kaluza and Klein. It's an extraordinary idea, but there are some physicists who believe we are living in a 10 or 11 dimensional world. The reason we don't notice the extra dimensions they claim is that they are curled up very small, so their effects are only felt indirectly. The universe may have started with 10 or 11 equal dimensions, but at some stage a number of them collapsed, leaving the 3 dimensions of space and 1 of time that we see today. If these ideas are right, then the history of the universe begins with just one thing, a multidimensional field which is the ancestor of all today's particles and forces. Quickly, the cooling universe loses its extra dimensions. The single force splits into 4, and in 15 billion years, we observe the results. There's one other thing that physicists demand of a fundamental law of the universe. It must provide a unique description of just one kind of world. This would mean that if science were in possession of the true fundamental theory, you could ask whether the laws of physics could have made the sky green and the trees blue. And the answer would be no. These things are not possible. The fundamental theory says that there is only one way for things to be. Some of the new theories seem to have that property of uniqueness. They achieve it because the constraints of symmetry narrow down the choices open to the scientists.
Well, physicists have very fertile imaginations, and so there are lots of different theories they could think of which might correspond to the real world. And so to narrow down the choice, we like to invoke this idea of symmetry in the hope that we can eventually pin down the correct theory. And as a crude analogy...
Even then, you have to be persuaded by their mathematical elegance. Not everybody is. Sheldon Glashow looks at these new developments with skepticism.
It's just some kind of abstract elegance. In fact, I'm thankful to supersymmetry because there are something like 1,000 high-energy theoretical physicists in the world. A large fraction of these people are working on supersymmetry. That keeps them out of my hair, leaves some room for me to do other things which have a better chance of working out. Many of my friends have been doing supersymmetry for the past 20 years. It's a vast endeavor, it's a fascinating theory, it's an ingenious theory. It has accomplished, in terms of explaining phenomena, absolutely nothing. It does predict the existence of new particles, and in fact, as you know, there are 17 particles in our bestiary at present in the standard theory. It doubles them. It says there are precisely 34.
The vibrating string is now in a different internal state, and so exhibits new attributes. It may have a different charge, or even a different mass. To a distant observer, it seems like a totally different particle. Strangely enough, many of the mathematical problems that have plagued all preceding attempts at fourfold unification disappear with this picture of the universe. But the ideas being explored by superstring theory have no chance of direct verification. So the only way for physicists to judge the quality of this theory is from its low-energy predictions, mathematical consistency, and internal elegance. In physics, simplicity and elegance are allied to beauty. Keats' famous line, "Beauty is truth, truth beauty," is actually borne out in the practice of physics. It doesn't just... The problem is that it only takes one contradictory experiment to disprove a theory. And when the stage is reached where theory has gone beyond direct experimentation, scientists will be left wondering whether their ideas were beautiful enough. That's Abdus Salam's warning about Kaluza-Klein and multidimensional theories.
I must confess that one cannot say that the aesthetics of man are the same as the aesthetics of the Lord. They may be very, very different. I would not like to say that this is the final theory, but I would like it to be correct, if it's possible, to test it properly.
Since 1983, the experiment which confirmed the electroweak theory has begun producing new data which doesn't fit in with any theory. News from CERN, announced by Carlo Rubbia, is the observation of some strange new effects, some surprising anomalies. The events in question are characterized by an unpredicted imbalance in the particles produced, more off to one side than to the other. This cannot be reconciled by today's standard model, and if true, implies that the model may be incomplete.
So far, there are about 5 very curious new types of phenomena that have been reported from CERN. Some of them are called Zen events. They're events where particles come streaming out in one direction, nothing comes out of the other side, the sound of one hand clapping. It's a strange business, and these curious anomalies simply don't fit in the standard theory. They're not part of it. They strongly suggest to me that we may be missing something very important. Perhaps one possibility is another kind of force, a force above and beyond the weak interactions, the electromagnetic interactions, and the strong interactions, and different also from gravity. A new force, the fifth force. Perhaps we are just getting a dim view of the fifth and perhaps the most important new force at high energy, from Carlo Rubbia and his work at CERN. If there's a fifth force, we'll have to put that together with the other forces. We'll have to make a fourfold unification before we can make a true unification of all the forces with gravity. Things might get a lot more complicated before they get simple.
On the other hand, there is a truly remarkable possibility. Excitement is mounting that buried within the debris that produced the W and Z may lie the first traces of one of the extra particles predicted by supersymmetry. Could the new data from CERN be the first evidence of a photino, or a slepton, or a squark? Or could it be something that will force physicists to revise their ideas completely?
Well, I think it's highly improbable that you get such a good idea.
It could be years before an answer is found. The solution to this and other puzzles may only come with the creation of even higher energy. In the United States, plans are already underway for the Superconducting Super Collider, or SSC. This accelerator will cost $3 billion, and if ever built, will consist of a circular tunnel as much as 100 miles long. Superconducting magnet technology would drive and steer the particles on their epic journey, ending in collisions with energies as much as 80 times as great as the events which are producing today's puzzles.
Well, people often come to me and they say, what is this that you're doing for? Why should the United States government spend millions and millions of dollars to build a new machine? Will it lead to a new kind of toothpaste or something like that? And I have to say to them that mostly the answer is no. What I usually say is this. I say that people differ from other animals in that they have curiosity. They look at the stars with wonder. We might try to teach dolphins and chimpanzees to speak, and sometimes we're successful, but they're sure not going to look at the sky and imagine constellations. This is the way in which people, or at least little children, differ from animals. Little children are curious. My kids ask me, where does the sun go at night? And how come I can suck a soda up through a straw? Questions like this. Later in life, they are trained not to ask questions of this kind. Not all of them. Some of them maintain this primordial human quality of curiosity. Some of these people become artists, like the man who made that. Some become composers. Some become physicists. Some become astronomers. These people, in a sense, have kept the faith. They really want to know what's going on.
It's hard to imagine a time when all our questions will be answered, when there are no more puzzles to solve, when most physicists are agreed on the nature of the universe. And even if they think they've found out, how will they know if they are right? As long as these questions remain, the search for the ultimate theory will continue.
Stay tuned for a look at the martial arts in Japan, following station identification. And join Jacques Cousteau and the crew as they explore the return of the sea elephants. That's Thursday at 9 p.m. here on TV 12.
For a transcript of this program, send $4 to Nova, Box 322, Boston, Massachusetts, 02134. Please be sure to include the show title. To purchase film or video copies of this program for educational use, call toll-free 1-800-621-2131. In Illinois or Alaska, call Collect, 312-940-1260. Major funding for NOVA is provided by this station and other public television stations nationwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials. And the Johnson & Johnson family of companies, supplying health care products worldwide.
Diamond State Telephone and its employees are proud to help bring you Nova on TV 12. And every day, we're putting our name on the line for you with signature service.
At PSFS, we believe an investment in knowledge is one of the best investments anyone can make. That's why, as a service to you, we're proud to help bring you this broadcast of Nova.
This week, the intoxicating intrigue of Okefenokee. Okefenokee, Wednesday at 8 on TV 12.
When you plan your vacation this year, remember this. If you love America, you're bound to love Virginia.
Virginia joins you in supporting TV 12.